So today we're going to be doing the 2012 Calc BC FRQ number 2. So the problem reads, for t is greater than 0, a particle is moving along a curve so that its position at time t is given by x of t, y of t. At time t equals 2, the particle is at position 1, 5. It is known that dx dt is equal to the square root of t plus 2 all over e to the t, and that dy dt is equal to sine squared t. So now this whole particle business is a little bit too boring, so let's think of it in slightly different terms. Let's think of this black line as being our unknown curve and the car as being our particle that is moving along this given curve. Let's go back through some of our givens. So we were told that at time t equals 2, the particle is at 1, 5. Also, we were given dx dt and dy dt. So we were not given the position function, we were given vectors. And specifically, we are given not position vectors, but velocity vectors. So we have to think of the vectors as this, as two arrows, one where it is moving forward and one where it is moving upward. So upward would be the speed, the velocity at which it is moving along the y-axis, and the horizontal arrow is the velocity at which it is moving along the x-axis. So the vertical arrow, dy dt, the horizontal arrow, dx dt. Okay, so coming back to the question, let's look at part A. Is the horizontal movement of the particle to the left or to the right at time t equals 2? Explain your answer. And find the slope of the path at the particle at time t equals 2. Going back to our little drawing, what we're trying to find out is if the car is moving to the left or to the right at time t equals 2, and what is the slope of the path of the car at this time. We can think of this as trying to find the red arrow here, the slope of the path at this point, or the slope along which the car would be moving at this point on the curve. So for the horizontal movement of the particle at times t equals 2, we're going to look at dx dt. Since it's a velocity, whether it's positive or negative is going to tell us whether the particle is moving to the right or to the left. So all we have to do is find dx dt at t equals 2. We can see, since the value we get is a positive value, that the particle, or the car, is moving to the right at time t equals 2. For the slope of the path of the particle, we're going to have to remember how to do slope for our vector value functions. So all that's going to be is going to be dy over dx. The way that we do this is we take dy dt and we put it over dx dt. Evaluating this new expression at 2, we will get the value which corresponds to the slope at time t equals 2. Part B asks us to find the x-coordinate of the particle's position at time t equals 4. So with our little car, it would look something like this, an unknown x value at t equals 4. Since we are given our little car's position at t equals 2, we can use the second fundamental theorem of calculus to find the car's position at t equals 4. We're going to take an integral from 2 to 4 of dx dt, and then add the particle's position at time t equals 2, which is 1, and the result will be the particle's x position at t equals 4. Luckily, this is a calculator problem, so evaluating the integral is easy. We just have to be sure not to forget to add the x of 2, because otherwise we are not going to get the accurate x of 4 value. Part C asks us to find the speed of the particle at time t equals 4, and the acceleration vector of the particle at time t equals 4. So for the speed, we're just going to apply the speed of vector value functions, or how to find the magnitude of the velocity vectors at t equals 4. So what we're going to do is find the square root of dx dt squared plus dy dt squared, and then plug in 4 for the value of t. Again, we are going to use our calculator to evaluate to the final answer. It's relatively straightforward, no integral or anything, but we just need to be sure that we are squaring them individually and not together, because that can be a mistake that is really easy to make and that will lead you to a completely false answer. As long as you keep everything in check, you should be able to easily get to the correct answer, which is 0.574504. For the second part of part C, since we know that acceleration is simply the derivative of velocity, all we have to do is take the derivative of the two velocity vectors we are given and then plug in time t equals 4. Again, the fact that this is a calculator question makes our lives much easier because rather than having to manually differentiate, all we have to do is plug it into our calculator. Make sure that this is something you know how to do before going into the AP exam or into any test because it will allow you to save so much time on calculator problems where you need to differentiate something at a certain point. The final part D asks us to find the distance traveled by the particle from time t equals 2 to time t equals 4. This would look a little something like this. We're trying to find the exact distance, or the arc length, between the position of the car at t equals 4 and t equals 2, so the distance that it traveled between those two times. So we're going to use the integral expression for the arc length of a vector valued function. Setting it up will look a little something like this. The integral from 2 to 4 of the square root of dx squared plus dy squared dt. Luckily, since this is a calculator problem, we can just plug this into our calculator like we did with the other integrals from the previous parts. As always, we have to be sure that we're inputting everything correctly into our calculator. Otherwise, we're going to get some very wrong answers and we won't get that credit point at all since there's no work to be shown. Now let's use the scoring guide to check our work. So for the first one, 1 point is given for moving to the right with reason, which we have, so check. Another point is given for considering that dy dt over dx dt, which we also have, so check. And then a point for the answer, which we have correct. So there's another point. For part B, there's 1 point for the integral and 1 point for the answer. So we have our integral, and then we have the point for the answer. So we would get 1 point if we had forgotten to add that x of 2, but we would still only get half credit on that problem. For part C, the breakdown is really easy. It's just 1 point for the speed and 1 point for the acceleration. So this is where there's a downside with having calculator problems, because we don't get any credit for the work. So if we are off in the answer at all, we just don't get the points. Thankfully, we were right, so we got both of those points. For part D, the breakdown is 1 point for the integral and 1 point for the answer. So if we make a mistake in evaluating or put it into our calculator wrong, we still have a chance at getting half credit. Here we have both correct. So we got full credit on the entire FRQ. Good job! If you think that some more practice would be helpful, you can search vector valued functions, and the worksheet from Eaton Math has some really good practice problems. Particularly, I think that the 5th and 6th arc length problems are really good. So if you want to try to find that, you can just Google the title of this worksheet or search vector valued functions and go until you find the one from Eaton Math. I hope that all this was helpful. Thanks for watching!